All right. On to our next person. Our next person is Robert Millikan. You might recognize his last name. He is related to Dean Amy's husband's family. So Robert Millikan is an American student. You know how people tend to think about like certain subjects as being like harder or more prestigious than others? Like we might talk today about like people who are like rocket scientists or brain surgeons being like extra smart, and that's like the hardest possible subject. So anyone who does that must be incredibly brilliant, right? You know how we do that? In his day and age, it was the classics that's like the brain surgery, the super hard subject, the thing that's really high status. So, Robert Millikan is studying the classics, which in his day and age is like, that's the thing that's really prestigious and hard. His classics teacher is like, hey, Robert, we actually need somebody to teach an introductory physics course. I know you've never studied physics before, but you're absolutely crushing it in my classics course, which is clearly the hardest course that anyone could possibly take. So if you are doing such an amazing job at understanding, Greek and Latin and, ancient Greek and Roman myths and translating the Iliad and the Odyssey and things like that, the hardest possible subject that could ever exist, surely a little thing like physics will be no difficulty to you. And I can ask you, a student at this university, to just be a professor for this little physics course that everyone knows is an easy class. And Millikan's like, yeah, sure, I can do that. I'm studying classics. This is the hardest possible thing. If I'm doing great here, clearly I can take on being a physics professor. And so he starts teaching an introductory physics course while he's still a student at this university. And as he's doing this, he's like barely staying ahead of his students because he's learning the material immediately before teaching it to them. And he falls in love with the subject. Yeah. He realizes, oh, actually I love this. This is great. And he drops out of the classics department, decides to become a physicist, and that's what he goes on to study. Now, Millikan is going to be studying electrons, these little things that J.J. Thomson has discovered are a part of every atom. And in particular, he's trying to figure out the charge of a single electron. We already know that electrons are negative. We know that electrons are tiny. What we're trying to figure out is how negative is a single electron. The problem here is you can't pull out one electron to measure. Right? That is a thing that we can't really do. So what he's going to do is he's going to do an experiment that's going to look at whole groups of electrons and see how negative different batches of electrons are. This is called his oil drop experiment. So I want to remind you, electrons have a charge. They're tiny magnets, effectively. And we can pull on those electrons with magnets. And Robert Millikan has an electromagnet, and that electromagnet's going to let him figure out how much charge he's pulling on something. At this point in the year, I suspect most of you have seen my floating globe. And you know that my floating globe works because we have a balance. So there is a force of gravity pulling that globe down, and then there's a magnet pulling that globe up. And when we get those forces exactly balanced, we can prevent that object from moving anywhere. So it's just like hovering in midair. That's the same principle that Millikan's going to use for this experiment, right? So his oil drop experiment looks like this. He's got a big, drum, and he has a spray bottle. Here it's labeled atomizer. That's just a fancy word. It's a spray bottle. He's got a spray bottle. It's got oil droplets in it. The oil is charged, which means it has, each drop of oil has some mysterious number of extra electrons in it. He doesn't know how many extra electrons are in each drop of oil, and each drop of oil is different. It's like you've got a whole bunch of bags of marbles. You have no idea how many marbles are in each bag, but you're trying to figure out how heavy is exactly one marble. So here is what he does. He spritzes out some of this oil into this thing. The oil drops begin to fall down here. And then he has this battery. He turns on the battery and he can control how much voltage, basically how negative, this magnet, it's got an electromagnet up here, is. So he can control how strong the magnet that's pulling upwards on these drops of oil is. So he fiddles with, he looks through a microscope, you can see a single drop of oil, and he fiddles with this battery until he can get one drop of oil to float, hover perfectly. And he can write down, oh, well, how strong of a magnet, how much charge did it take to make that one drop of oil float? And so he writes down, here's how much charge it took to make this drop of oil float. Now, it's not super useful on its own because he doesn't know how many electrons are in that one drop of oil. So that charge is coming from a totally unknown number of electrons. But then he keeps doing this. He finds another oil drop, focuses in on it, adjusts his electromagnet until he can get that one to hover exactly. And then he records, here's how much electricity it took to make that one. Here's how much charge it took to make that one hover. And he does this over and over and over again. So I want to take you back to this metaphor with the marbles. Imagine you have a bunch of bags of marbles. You have no way of knowing how many marbles are in each bag. But you can measure the mass of the bag as a whole on a scale. And you do this, and you get a bunch of different charges. So one bag full of marbles, you say is, okay, well I measured this bag and it's 49 grams. And then you measure a different bag and you're like, okay, this different bag is 98 grams. And the next one is, oh, this one's 70 grams. And then there's one that is 56 grams. Can anyone tell me how heavy a single marble is? So each of these bags is different numbers of marbles. You don't know how many marbles are in there. But how heavy is one marble? Joaquin?
Because of 1 gram.
That's a possible answer, although you would expect if they were 1 gram each, you would have some numbers that are more in between these. Let's go to Carter.
7 grams.
7 grams, right? So this bag must have 7 marbles in it. This one has 11 marbles in it.
But it's doubled. So it's 14.
Oh, you're right, 14. Thank you. Math. This one has 8 marbles. This one has 10 marbles. So we can figure out the mass of a single marble because all of these measurements are multiples of that same number. And we can assume, even though, yes, all of these are multiples of 1, we would, if you had lots of measurements, you would expect to see some things that are multiples of 1 that aren't multiples of 7. So he can measure the charge of a bundle of electrons, and all of those charges are multiples of the same number. So he's able to figure out the charge of an electron. Yes?
So to figure out how much one marble weighs, you have to divide the mass by 7.
Well, he basically figures out that each marble is 7 grams because of the fact that all of these things are multiples of 7, right? Although what he's doing this with is with charges instead of mass, basically saying how negative is an electron. And the numbers are way bigger because each drop of oil is going to have hundreds, thousands, tens of thousands of extra electrons in it. Yes.
Theoretically, couldn't each marble be 1 gram?
Theoretically, but you would expect if each of these was 1 gram, if you had a bunch of random bags of collections of marbles, you would expect to see some bags that weren't multiples of 7. If I'm just grabbing fistfuls of marbles and putting them in bags, and it's random, you would expect to see some numbers like 12, right? 16, 92, numbers that aren't multiples of 7. So it's incredibly unlikely if these bags are just randomly determined that you would have all of them be multiples of 7 and none of them not be multiples of 7. And again, the idea of the bags of marbles, that's a metaphor. We're not literally weighing bags of marbles. He's figuring out the charge it takes to get an oil drop to float. That's the measurement he's writing down. Yes, ma'am?
Charge of a single electron.
Oh, Lord. Let me get that number for you. It's not a number you need to know. It is a very, very tiny number.
Did
do
he
have it.
find the same number? Or
Did he
was,
find the same number?
Was he close?
Yeah, he gets this correct. The answer to your question is 1.592.
Wait, Hannah?
Yes.
The ratio that J.J. Thompson found was mass and what?
The mass and charge of an electron.
Yeah, and then
Basically, J.J. Thomson has the constant of proportionality between the mass of an electron and the charge of an electron.
And then Millikan discovers the charge?
Yes. Which means that we now can figure out the mass exactly. So the charge of an electron is 1.592 multiplied by 10 to the negative 19, which basically means divided by 10 19 times. So really you'd have to like move this decimal to the left 19 times. And the unit there is coulombs. But in chemistry, we say the charge of an electron is -1. So -1 for the charge of an electron in chemistry.
Oh, because hydrogen is one. So
Well, no, the mass of hydrogen is 1. This is charge. So charge and mass are different things.
Yeah, but why would you
The
say
charge of a hydrogen atom would probably be 0 for most things, right? Unless it's lost an electron, in which case it would be +1.
But why would you say that it's -1 if it's not even 0?
because it's negative charge.
I don't understand your question.
Oh.
Electrons have a negative charge.
Oh.
So in chemistry, we don't want to bother with units like coulombs. We just talk about an electron is -1. Protons, which at this point in time haven't been discovered yet, are +1, and neutrons have a charge of 0. So neutrons are neutral. Protons are positive, those would be +1. Electrons are negative, those would be -1. All right.